Now let's set up the equilibrium equation for the standard beam element. We went up to starting with the strain energy of the system, we got the stiffness matrix and the displacement vector. Now the description of the equilibrium equation also contains the force vector, as I showed you before. So the derivation of the force vector for the beam element is not as straightforward as in truss elements, because in truss elements you have only 1 degree of freedom where the force is acting. Well, you could have 2 degrees of freedom where the force is acting if the truss is lying in a 2D plane. But basically it's always concentrated forces at the nodes. Now in terms of beams, we can also have distributed loads. So that's what we are going to pick up. So we'll take, for example, a external force, because the strain energy is basically because of the internal force or the resistance of the material. And now the external force that is acting on the system is a distributed load, or a uniformly distributed load in this case. And this distributed load can be written as W of X. So the work done by this external force, W, is given as integral over the length of the element, W times V times X, where V is basically the displacement in the transverse direction, because the load is also acting in the transverse direction. Now you may also have realized that in a pure bending beam you also cannot have forces that are acting actually. You always have to have out of plane forces which are then derived into moments, etc. Now in this work done relation, we can substitute the V, which was derived as an approximate behavior function, which can be given as N times U. Now we know that the N is the only one that's actually depending on X. So if we integrate N over L from 0 to L, then we will get, I'm not going to do the integration now, but what you will get quite easily is W times L by 2. You can write this also as a vector, L square by 12, L by 2 minus L square by 12 times U, which is the displacement vector. Now to arrive at the equilibrium equation, we have to take the negative of the external work done of the system, and then it has to be minimized to the with respect to each of the nodal displacements, right? So if I have the force vector F, which is given as Fi1, Fi2, Fj1, Fj2, then that can be given as minus partial derivative of the work done by Ui1, partial derivative of with respect to Ui2, partial derivative with respect to Uj1, and partial derivative with respect to Uj2. We could also of course do it in the way we did it for displacement before, which was quite easy, and we said okay, we are just going to do it with respect to U over here, and that will be gone. But well, we can also do it in this way. I just wanted to show you a couple of examples. So what you would have left in this case is basically W multiplied by each of these terms over here, and the U will be gone because you are partially differentiating it with respect to W, and of course the negative sign. So what you get is minus WL by 2 minus WL square by 12 minus WL by 2 and WL square by 12. So if you look carefully, going back to your beam element, this node, this displacement, I'll name it as 1, 2, 3, 4. You have 1 acting here, 3 acting here, 2 acting here, which is clockwise, and 4 acting here, which is positive, so it's anti-clockwise. If you had a weight distributed load W everywhere, and the length of the element was L, then of course the components of W acting at 1 and 3 would be WL by 2, which checks out. And the moment because of WL by 2 at these two lengths will be given as WL square by 12. So it's quite easily checked that it's also in equilibrium. So this is your force vector. So if I put finally everything together, then I will have Ku is equal to F as my equilibrium equation for a pure beam under bending.